So we will continue with the lecture on Chapter 2. This is the third lecture for Chapter 2. We will be discussing the section on insurances payable at the moment of death and the relationship of Z and T with respect to their PDF and CDF. So, the payments of the benefit are due at the end of the year of death. So that's our assumption now, since we would like to get the insurance, we would like to discuss the insurances which are payable at the end of the year of death. The year is considered not calendar years, but instead it is from birthday to birthday of the insured. Okay? And our random variable Z, which is the present value random variable for the benefit of the insurance, will now be dependent on the random variable K instead of T, because we are now considering the discrete case. So our benefit function we will denote by B sub k plus 1 and the discount function by V sub k plus 1. And our random variable Z now will still be the product of the benefit function and the discount function. Okay? So let's start off with the whole life insurance. Again, this is an insurance that will provide a benefit, payment of benefit upon the death of the insured anytime in the future. So when the insured dies during the first year, K would be 0. If the insured dies during the second year, K would be 1, and so on. Okay? So the discount function would be V to the K plus 1. We take note that it's K plus 1 and not K, right? Because if the time of death is T, and then the greatest interior value of that is K, but then the payment is paid at the end of the year of death, so that would be K plus 1. So that's why our subscript and our exponent here is K plus 1. And of course, the benefit is 1 unit. So we're assuming that the benefit size is 1 unit. So Z now would be again B times V. So it turns out to be V to the K plus 1 whenever K is 0, 1, 2, 3, and so on. So the expectation of Z, which is again called the net single premium for this particular insurance product, is the summation of V to the K plus 1 times the probability mass function of K, since our random variable Z now is dependent on K. So we have to use the summation because it's discrete, and of course the probability mass function of the random variable K. And one of its forms is KPX QX plus K. So this summation gives us the net single premium, and we will make use of this representation for that. Take note of the absence of the bar on top of capital A. That would mean that the insurance is payable at the end of the year of death. And the variance will also be written this way. And then this would be the second moment of Z, and we can again use the rule of moments. So the e to the delta is going to be replaced by e to the delta k plus 1 will now be replaced by e to the negative 2 delta times k plus 1. Okay? For the n-year term insurance, again, we note that the benefit will be paid only if death occurs during the n-year term. So if k is 0, 1, 2, up to n minus 1, there will be a benefit of 1 unit. But otherwise, there is no benefit. So the discount function would be v to the k plus 1 for k from 0, 1, 2, up to n minus 1, and 0 otherwise. So Z will take this form, right? And so the expectation would be the sum of V to the K plus 1 times KPX QX plus K, where K ranges from 0 to n minus 1. And this will be the representation for this net single premium. Again, we take note that we don't have the bar on top of A, capital A, because that would imply that the insurance is payable at the moment of death. But this is an insurance payable at the end of year of death. For the n-year endowment insurance, again, the benefit is 1 unit for any K. but the discount function now is v to the k plus 1 if k is 0, 1, 2 up to n minus 1, and v to the n if k is n plus 1 up n plus 2 and so on. We take note that the benefit is paid at the end of n years if the insured is still alive during that time. So the value z takes this form, assuming again that the benefit is 1 unit, right? So z takes this form. And so the expectation of z will be the sum of these two summations. Okay? But then again, the second summation is actually b to the n npx. And then from our discussions earlier, this is the net single premium of an n-year pure endowment. And this is the net single premium of the n-year term insurance. We can see that this summation reduces to this using the following argument. If you look at this, this is the summation of the probability mass function of k, where k goes from n to infinity, right? So, of course, we can rewrite that this way. The first summation is from 0 to infinity. The second summation is from 0 to n minus 1. And we know that this is equal to 1, right? This is equal to 1. And this would be nqx. You can reduce that to nqx. And 1 minus nqx is npx. Okay? And then from the M-year, for the M-year deferred whole life insurance, again, we assume that the benefit is 1, and the benefit of 1 will be paid only if death occurs after the M-year deferred period. So when k is m plus 1, m plus 2, and so on, the benefit is 1 unit. And if k is 0, 1, 2 up to m minus 1, the benefit is 0. And the corresponding discount function would be this. And the corresponding value for z is defined as 0 when k is from 0, 1, 2 up to n minus 1. And v to the k plus 1 where k is from m plus 1, m plus 2, and so on. So the summation would be equal to this, or rather the expectation would be equal to this summation. And this would be our representation for the net single premium. Okay? Now, let's try to relate the random variable z and the random variable t. No? So again, in this particular slides, we assume that the insurances are payable at the moment of death because we're dealing with T. So consider a whole life insurance. Of course, we know that Z cannot be 0. Cannot be less than 0. So the event that capital Z is less than or equal to small z, where z is any number that is less than 0, is empty. Remember that z is equal to v to the t, right? And t is assumed to be greater than 0. Okay? And v is a constant which is between 0 to 1, right? Because v again is 1 all over 1 plus small I, where small I is your interest rate. So that would be from 0 to 1. If z is between 0 to 1, then the event that z is less than or equal to small z, as how we have explained last time, would be this event. T is greater than or equal to log of z all over log of v. This can be derived very simply since capital Z is v to the t, right? So we get the log of both sides, and then we divide by log of v. But log of v is negative, right? So that makes us change this inequality symbol from less than or equal to greater than or equal. And then if z is greater than or equal to 1, then the event that z is less than or equal to small z is going to be the universe. Right? Because, if this is the event that capital Z is less than or equal to small z when z is greater than or equal to 1. So that would be the universe. So the probability associated with these events would give us the corresponding CDF. of our random variable z in terms of the CDF of the random variable t. So when small z is less than or equal to 0, the CDF is 0. When small z is between 0 and 1, the CDF of z is equal to 1 minus the CDF of t evaluated at log of z all over log of v. And when z is greater than or equal to 1, the CDF is equal to 1. And so, the corresponding PDF, we just have to get the derivative, no? So the corresponding CDF of Z for a whole life insurance with a unit benefit takes this form. It's 1 over delta Z times the PDF of the random variable T evaluated at log of Z all over log of V, where Z is from 0 to 1 and of course will be 0 elsewhere. Okay? Let's use these formulas to look. We again use this function that we have encountered earlier, but this time we would want to determine the PDF and the CDF of Z, given that the PDF of T is this. And we're assuming, of course, that the insurance is a whole life insurance. But our T is only up to 80, right? Our T is from 0 to 80. Okay, so first we find the CDF of T. So evaluating the CDF of T, we get the integral of the PDF ds where s ranges from 0 to t. But then of course our t should be only between 0 to 80. So it turns out to be t over 80. And so the CTF takes this form, right? So the CDF of t, given the the PDF earlier, is 0 whenever t is less than 0. It's t over 80 whenever t is from 0 to 80, and 1 whenever t is greater than or equal to 80. Anyway, this also follows from the fact that the given PDF earlier is the PDF of a uniform distribution on the interval from 0 to 80. Okay? So, from this CDF, we can see that if we look at the value of the CDF for values of t which are greater than or equal to 80 as given here, no? It's going to be equal to 1. Okay? It's going to be equal to 1. So that tells us now that the probability that t is greater than 0 is equal to 0, right? Since t cannot be bigger than 80, so the probability that t is greater than 80 is going to be 0. And let's look at this event. The event that t is greater than or equal to 80, that would be equivalent to this. V to the t is less than V to the 80. Again, we take note that we need to change the inequality symbol because we're dealing with an exponential function that is decreasing, the base being V, and V is between 0 to 1. Okay? But then we know that this is Z, right? V to the t is Z. So this event here is actually the same as this event. Okay? So these two events are equivalent, so the probability associated with them would be the same. So the probability that Z is between 0 to V to the 80 is going to be equal to the probability that t is greater than 80, and we know that that is 0. Okay? So the probability that Z is between 0 to V to the 80 is going to be 0. Okay? So, that is, we put that here, right? Z is less than V to the 80 is the CDF is 0. Okay? And then we now look at the case when Z is between V to the 80 up to 1. So the CDF is given by the formula that we have. So that's 1 minus the CDF of T evaluated at log of Z all over log of V. But then we said that the CDF of T is T over 80. So we replace T by log of Z all over log of V. So we end up with this expression here. Okay? 1 minus 1 over 80 times log of z all over log of v. And so this gives us now the CDF of our random variable z, which was arrived at using the given PDF and CDF of the random variable t. Okay? And of course, we can just have to differentiate that CDF to get the PDF with respect to z. So we plug that in. So log of z is actually negative delta, or negative delta, or negative log of v is delta. So log of z, the derivative of that is 1 over z. 1 over 80 log of v is a constant. So we end up with this expression, right? So the PDF of z is 1 over 80 times 1 all over log of z, where z is between v to the 80 and 1. And of course, 0 elsewhere. Okay? And then let's consider also the other case that we used earlier, the M-year deferred whole life insurance. Oh, we take note of the following. So although t is continuous, z is a mixed random variable because it will have a positive probability at the point z equal to 0, right? We said that earlier because this event, the z is equal to 0, corresponds to this event in t, that t is less than or equal to m. So then, the mass point z equal to 0, the probability that z is equal to 0 is actually the CDF of t evaluated at m. Okay? So, if you want to get now, if this z, small z, is between 0, not including 0, and v to the m, so we have to break up this probability expression into two parts to get the actual expression for the probability of z, since we know that we have a mass point at z equal to 0. Okay? And then again, we note that z is b to the t. And from the discussions earlier, this event is actually the same as this event. So the probability of this event is this. Okay? So in other words, the CDF of z, given that z is the random variable for an M-year deferred whole life insurance, is given by this expression, which is an expression in terms of the CDF of t, right? 4 values of z in this interval, of course, right? So it is the CDF of t evaluated at m, and then this expression here is 1 minus the CDF of t evaluated at log of z all over log of v. Okay? And so, if you want to have the complete expression now for the CDF will take the following form. So, when z is exactly 0, the CDF is the CDF of t evaluated at m. And if z is between 0 to v to the m, it's this expression which we have earlier in the previous slide. And when z is greater than v to the m, the CDF is going to be 1. Okay? Let's consider this example that we had earlier, and now this time we want to find the CDF of z. So mu is 0.04 and delta is 0.10 for an M-year deferred whole life insurance payable at the moment of death, and then we assume that mu is fixed, it's constant. It's actually given to be 0.04. Okay? And then from the discussions earlier, we note that if the assumption on mu is that it's constant, the PDF of t takes this form, right? It's mu e to the negative mu t. And given that mu is 0.04 for this particular problem, or for this particular example, this would be the PDF of t. And if we take note, this is actually the exponential distribution. The mean, so our t has an exponential distribution whose mean is 1 all over 0.04. And since it is exponential, this is how its CDF would look like, right? So the CDF is 0 for all t that is less than 0, and it takes 1 minus e to the negative 0.04t if t is greater than or equal to 0. And so this implies now that the CDF of z evaluated at 0 is the same as the CDF of t evaluated at 5. So it's 1 minus e to the negative zero point 0.2. Okay? And then if z is between 0 to v to the 5th, then the CDF is from the formula earlier, it's the CDF of t evaluated at m, which is 5, plus 1 minus the CDF of t times evaluated at log of z all over log of delta, or log of v rather. So this is 1 minus e to the negative 0.2 plus 1 minus, again, t is exponential, so that's 1 minus e to the t. But t is this. So we just replace that e to the negative mu t rather. Sorry. Again, the CDF of t is 1 minus e to the negative mu t, right? Where mu is 0.04 and t is this, log of z all over log of v. But then we note that log of v is actually negative delta. And delta is given to be 0.10, right? So what we have is the following. So this one cancels out. You have 1 minus e to the negative 0.2 plus e to the negative 0.04 times log of z all over 0.10. So 0.04 divided by 0.10 is 0.4. And of course, e raised to 0.4 log z is equal to z to the 0.4. Okay? So in other words, the CDF of z now takes the following form. If z is equal to 0, it's 1 minus e to the negative 0.2. If z is between 0 to v to the 5th, the CDF is 1 minus e to the negative 0.2 plus z to the 0.4. And if z is greater than or equal to v to the 5th, the CDF is 1. Okay? So, I think I will end this portion of the lecture here. So, we'll continue with the next lecture. Okay?